space, and in 2, 3, 4, and 5-dimensional space. And let me see here. The objectives of this talk. Oh, I want to thank the members of ANPA for an opportunity to speak here today. I forgot to say that. Our objective today is to show how to use the methods of hyperplane cross-sections to visualize geometric objects in 4-dimensional and 5-dimensional space. And my intention is to avoid technicalities and focus essentially on the intuitions, give everyone a feel for some of the techniques, and in particular the technique of hyperplane cross sections. So I'd like to begin our story with Flatland. This was a book written by Edwin Abbott. Let's see here. This is blocking part of my screen. Put it there. By Edwin Abbott. He wrote it under the pen name of A Square, and it was published in 1884. It's a beautiful book. It's a satire on Victorian society based on mathematical fiction. The setting for this book is a mythical 2-dimensional kingdom Flatland called Flatland. The inhabitants are line segments, triangles, polygons, and circles. And there's a caste to the society. The larger the number of sides, the higher the rank. And of course, circles have the highest rank since they are the limit of polygons. The main character is, as you might note, the author of the book is A Square, which is the pen name for Edwin Abbott. The plot, on New Year's Day, A Square is visited by a sphere from Spaceland. In Square's living room, suddenly a point appears, grows into a larger circle, which then shrinks to a point and disappears. Square is now lifted up into out of Flatland, up into Spaceland by the visiting sphere, and comes to believe in higher dimensions. And of course, Square returns to Flatland, speaks of higher dimensions, and is eventually thrown into prison for heresy. It's a beautiful book. There's much more to it than this. He also visits point land and line land, but we will ignore these. So this is what A Square saw in his living room on New Year's Day. He saw a point suddenly appear, expanding into an ever-growing circle, then finally shrinking back to a point and disappearing. And as the sphere passed through the 2-dimensional plane of Flatland. And if we think about this a bit, this is an application of Morse theory. We have a height function, which maps the surface onto the real line, function f. And the inverse image of each point of the real line is a cross-section of, in this case, the surface of a torus. And we can also jiggle things a little bit so that all singularities are isolated and surfaces have essentially 3 kinds of singularities: peaks, as we see, valleys, and saddle points. These are called the Morse singularities. And so here is a Flatland movie of a torus in a non-standard position. It has 2 this is the torus itself in the position I just showed you. Excuse the graphics, but I need to improve that graphic. Okay, we'll be talking about this in the context of rubber sheet geometry. We have the Morse height function, and this is the distorted 2-sphere. Think of the surface of a ball as made of a rubber sheet, and we can distort it if we'd like. So if we take a look at this, so we have two saddle points. What we can now do, it's always possible to jiggle the surface so that all singular points are isolated. All right. Moreover, always possible to jiggle the surface so the singular points are isolated. But more than that, more importantly, we can do it in such a fashion that all saddle points are at the same cross-section, same level. And this will turn out to be of central importance, pushing everything into the same level. So in this case, what we've done is push the left saddle point down, the right saddle point up, so that now both saddle points lie at the same level, and our movie of the sphere passing through the living room looks as shown on the right. And in fact, there's something to be noticed here. If we have information, we call this section containing all the saddle points the midsection, we can throw away almost all the entire picture except the midsection picture, provided we have information as to how the saddle points open up when we go up or go down. And so we'll use the following labeling convention. If the saddle point opens up going up, and in this fashion, it's labeled by a mark, and in the opposite direction, it opens up in the other direction. So we'll use the following labeling scheme. So here is the Flatlander movie, and we're only looking at the midsection. We have actually reduced a three-dimensional problem to a two-dimensional problem. All the information about the movie is contained in this one single midsection view with the two labeling marks, and contains all the information. Gee, this thing is really in the way, isn't it? I can't do anything about it. Here's an example of a torus that you could see in Flatland. It has two singularities, and this will, you'll see basically a circle opens up and then comes together, merges at these points, and then opens up in a different way, finally converges to a point that disappears. There are, let's see, maybe I have another picture of this. Well, let me go back. Essentially a circle, there's one peak, one valley, and two saddle points. The Euler characteristic of this is simply the sum of the peaks and valleys minus the sum of the hyperbolic points is 0, so we know this is a torus. How can a Flatlander visualize a knot? That is a knotted circle in 3 space. Well, let's take a look at this. This is an interesting exercise. Here's an example of a knot. This is the trefoil knot, and a Flatlander, as the knot passes through the space, would appear to be a single point, which appears out of nowhere. It separates into 2 points. Now we see a third green point appears. The green point separates into 2 points. The green point now rotates around the black points. And finally, we have these 2 black points that I'm pointing to. I guess you can see my cursor twist around. And finally, the points converge, merge on the left and the right, and finally disappear. Okay, now what I'd like to do is to go to solid land. We have an intuitive idea from Flatland, and this is a typical inhabitant of solid land. And how can a solid lander visualize a knotted surface in 4-dimensional space? I find this an interesting question. Well, I was last New Year's, or the New Year's before last, was visited by a sphere in four-dimensional land, 4D land. And what I saw was the following. In my living room, I saw 2 points mysteriously appear out of nowhere. Each of the 2 points expanded into circles. The circles intertwined, combined at a hyperbolic point, and then separated, once again, combined at a saddle point, separated again into 2 circles, which shrunk to a point and vanished. This was a mysterious visit by it turns out, a sphere from 4-dimensional space. And now the whole point of this is the cross-sectional approach to viewing geometric objects in 4D space. Here's an example. If we go back to our example in Flatland, we can also view this as a cross-sectional view of a surface in 4 space passing through the hyperplane. And this is essentially a sphere. The number of peaks and valleys minus the number of hyperbolic points is 2, the Euler characteristic of a sphere. And the midsection view of, use the midsection approach. We'd like to reduce 4D knot theory to 3-dimensional knot theory. And we'll use the same approach we used in Flatland. And essentially, we push all the saddle points up into the same level. We can jiggle the surface, so this is so. So all the information is essentially contained in the mid-level, the midsection, provided all saddle points are labeled as to how they will open up above and below. And so we can now take a look at our visiting sphere from 4-dimensional space. We can push the saddle points into one midsection and end up with an image which looks like the following. 2 points appear, expand into circles. The circles intertwine, touch at saddle points, and then open up in the opposite way. And eventually circles shrink down to points which suddenly, poof, disappear out of nowhere. So this is another view of an inhabitant of 4-dimensional space. And we mark these saddle points with labels indicating what happens as we go up or we go down. I guess we can think of that as time as our 4th dimension. And in this way, using our labeling scheme, the marker shown here shows how things will open up as you move up, and you do the opposite when you move down. Try to use a very intuitive labeling scheme so it would be easy to remember. So here is our, once again, this is our distorted 2-sphere that is actually in 4 space. And here, if we go back to this, this is now a midsection view of our 2-sphere visitor, a knotted 2-sphere lying in 4 space. Unlike Flatland, there's no knotted 2-spheres do not exist in 3 dimensions, but they do exist in 4 dimensions. Here's an example of a space. I guess I was going to ask people to guess what space this is. It opens up to a single loop above, which vanishes, and a single loop below. This is basically real projective space passing through the midsection, our 3-dimensional hyperplane that we're living in. So this is an example of the space. And once again, no need to work with the rest of the movie. We can actually keep only the midsection and work with that. We can reduce a 4-dimensional problem to a 3-dimensional problem with the proper notation. The other notation is there's a lot of information you can compute with these diagrams, but I'm not going to do that. I'll talk about it. So this is an example of embedding of RP2, real projective space, into this. The beauty of this is that there are midsection moves on our representations of knots, our 3-dimensional representations of surfaces in 4 space, which enable us to reduce this to an entirely 3-dimensional problem in 3-dimensional knot theory. And here are, of course, the Reidemeister moves that we can actually apply to the midsections. We've seen these before. They do not change the knot type of the knotted surface. And there are some additional rules to deal with the labeled saddle points. These are actually moves. There are five of them. These are called the Yoshikawa moves. And it takes a little time to get used to them, but essentially there are now 8 different moves that we can use. The beauty of this, that this tells us everything. The Reidemeister and Yoshikawa moves on the midsection representation of 2 knots preserve knot type. It's the same surface, knotted surface, no matter how we do the moves. And the beauty of this is that perhaps I'm going too fast. If there are any questions at any time, please feel free to ask them. Swinton, Cureton, and Curlin proved a very important theorem. 2 knotted 2-sphere midsections represent the same 2-knot if and only if there's a finite sequence of Reidemeister and Yoshikawa moves which transform one into the other. Now this is quite a nice result. We've reduced 4-dimensional knot theory to 3-dimensional knot theory with this one little theorem. We only need to work with midsections. Now, maybe I should pause for a second. I'm going to talk about a visit from a 3-manifold in 5-dimensional space. But before I do that, are there any questions from anyone? I guess not. So let me continue. This is what happened when I was visited last New Year's. I saw actually a 3-manifold pass through my living room. And this is an object that exists in 5-dimensional space. And you can see that this is a movie of movies. A lot is cut off by this zoom label up here, but essentially we can think that there are 2 additional dimensions. We're dealing with 5-dimensional space, and we're looking at, so we can think of the 4th dimension as being time, and the 5th dimension as being hypertime. Time for us is vertical, and horizontal time, hypertime is horizontal. So what we're looking at is a very interesting movie. An inhabitant of 4D land would simply see a movie of 4-dimensional cross-sections, hyperplane cross-sections of this 3-manifold in 5 space. Each row can be thought of as a movie for someone living in four-dimensional space of basically four-dimensional cross sections. Now, we live in three-dimensional space. So in order to visualize an object in five space, each four-dimensional movie has to be broken down. Each frame of a four-dimensional movie has to be broken down into a three-dimensional movie. And that's essentially what's happening here. Each of these vertical columns represents a movie. As you move from left to right, each vertical strip represents the higher dimensional movie. We're actually looking at an object in five-dimensional space. Codimension 2, it's a dimension 3, 2 dimensions less than the ambient space. This looks very complicated. And at first it does, but surprisingly, this simplifies. It looks hopelessly complex. As it turns out, only three key frames are needed in this movie of movies, provided they're suitably labeled, and I've highlighted them here. This is most amazing. We can represent an object, a three-dimensional object in five-dimensional space with three labeled frames in our movie of movies. Let's take a look at this a little bit. First of all, let's try to simplify things a little bit. Let's begin by noting that there are four types of Morse singularities, respectively of indices 0, 1, 2, and 3. We solved for surfaces. There are only three singularities: peaks, saddle points, and valleys. But now we have peaks, two types of saddle points, and valleys. And let's take a look at what these singularities look like. Local movies of movies. So these are local movies. Maybe I should call these movies squared. Of these singularities are now given in the following four slides. Here is an example of a singularity. Let's look at the top part. Each rectangle in the top diagram indicates three-dimensional frame. So this is a movie of nothing. A point appears, and then it expands into a sphere. And if we write that as a local movie of movie, it looks something like this. So this is a local movie of movies of a singularity of index 0, just simply a sphere that's opening up. The next one's a very interesting one. This is one of the two type of saddle points that occur. And as we look at the cross sections, we've pushed, you'll notice that the top is each square or rectangle at the top represents a three-dimensional cross section. And we're looking at a surface, two portions of the surface in frame -1, which touch each other in frame 0, and then separate into a surface that is shown below. And you'll notice that these movies have been normalized. We've pushed all the saddle points of the surface on the right into the same midsection. And as a movie of movies, this is what it would look like locally, as shown here. This is time, this is hyper time, and this is a local movie of the singularity. Okay, now here's the other one. It's simply another singularity. It opens up in the opposite direction. And we have a local movie of movies here. And finally, the other point is when a sphere suddenly shrinks to a point and then vanishes. This is the fourth kind of singularity. Okay, what we'll do is devise a labeling scheme for the two saddle point singularities. The peaks and valleys don't matter. We can push all the singularities into two levels. The top index 1 singularities will be in one cross section, and all the other index 2 singularities will be in a second cross section. And we can label these singularities, these saddle points, as so indicated. Here's one. This is a labeling scheme for the index 1 singularities. This is a labeling scheme for the index 2 singularities. So unlike the solid land, excuse me, I am in solid, unlike in Flatland, we only had, for surfaces, we only had two singularities, two saddle points. We now, one saddle point, excuse me, we now have two, and we have two midsections that we have to deal with. And here they are. Here is the midsection at time -1, 0. That's time and hypertime. And here is the section between them, the four-dimensional cross section between them. And here is the four-dimensional cross section or midsection just below. This represents, in 3 frames, this is most amazing, a 3 manifold. It can be very complex in terms of simply 3 frames. More details of this can be found at the following paper. This is on my website for those that are interested. It's 5-dimensional knot theory. And that's it. This is so let's see, I guess I will open everything up to questions. Are there any questions?
Okay, thank you very much for that, Sam.
Well, thank you.
Let me get my video back up.
I didn't realize it would be that short.
Here's a question. Some of my favorite 3 manifolds in 5 space are the Britzkorn manifolds, the ones given by an algebraic variety with 3 exponents, like x to the 3 plus y to the 5 plus c to the 7. Did you ever figure out the movie for them?
No, it's a great idea. I like that idea. A movie of those I'd like. That's a good project. Now you wrote your dissertation on those singularities, didn't you?
Mm-hmm.
Oh, yeah, that's really interesting. And Milner has done a lot more there. I could have presented a lot of the technicalities of computing the different algebraic groups, the first the fundamental group and the homotopy groups. And there are many algebraic invariants associated here, but I wanted to keep the talk very technical. I had no idea it would only take 30 minutes. Thought it would take longer.
Any further questions?
Yes, I have one,
Richard?
please. Do you have any motion picture type movies of some of your 2 or 3 dimensional images of the 5-dimensional device you just showed us?
Oh, I showed you one. You mean you would like some more?
I was a few minutes late. Yes, I'd like to see something actually moving.
Oh,
Oh,
you're
okay,
looking for an
good.
animation.
I'm looking for an animation and then maybe have the symbolism next to it so I can make a direct connection between the two concepts.
That's a great idea. You actually give me a lot of work to do. I'll be sure to do that. I haven't done that, but in the PowerPoint you can, and that will take a little more work. I intend to do that. I can show you a few other things here, if
Please.
I may. I have another picture of that same three manifold embedding. In the paper in on five-dimensional knot theory I mentioned, I did compute the second homotopy group of that, as well as the fundamental group, as well as something known as the K invariant. But let me just, if I may, just share the screen and show you some other pictures here. Let me get out of this. How do I get? I have to unshare, excuse me a second. Something glitch, and let me stop the share for a second.
It says you've started screen sharing.
Yes.
Well, that's stopped.
Yeah.
That stopped screen sharing.
It's multiple participants can share simultaneously. That's what you need. So it's okay on my side. Sam, you are muted.
You're muted, Sam. Muted.
Mute? I'm unmuted, thank you.
No, okay.
I can share the screen to show you another movie. Unfortunately, they're not in motion. That will take a lot more work. But let me see, there's one more thing I wanted to show you. If I may. Here it is, and where am I? Here it is. And I have some other movies here, if I can find them. Nope, where's that? What in the world? And I must be here. And you can actually simplify the movie I mentioned below. Here's a simpler version of the same movie. This three manifold I showed you in the example is unusual in that you can actually push the two side frames into the center frame of the movie, and there's only one cross section that you need to look at. It's most amazing. So that whole thing can be represented by one cross section, which is given here. That represents a three manifold in four space. It's most, to me, I find that amazing, because it's not true of everything. And actually, I guess that's about what I have. Let me get out of this. There are other calculations you can make on this. I didn't want to become too technical this time. There's some strange things that happen here. Let me stop the share. As it turns out, if you look at the complement of the three manifold in phi space, you can break it up into what's called a gem complex. Now I'm getting technical, where the space itself is the union of two spaces, which are Eilenberg-MacLane spaces, and they intersect in an Eilenberg-MacLane space. Because of that, you can actually make a lot of interesting calculations. I hope I'm not getting too technical. Any other questions? someone's given me homework here. Thank you. I will try to make that into a movie. There is, that will take a lot of time though.
It might be worth mentioning that there are movies of almost things
Questions?
about, oh, maybe you can't, can you hear me?
Well, thank you very much. It's been a pleasure. And if you have any questions, you can always reach me. Oh, there are
I
questions.
think
see
Lou was
hands
saying
up.
something. Lou was saying something.
Sam, for people who are interested in
Let's
movies,
see. I see hands.
Sam, can you hear me?
Can you hear me?
Yeah, I can hear both of you. I can hear
I
both
think
of you.
Sam can't hear me, so I'll leave it off.
I cannot hear anyone.
Oh.
Hello?
Perhaps you can put questions into chat.
Hello?
Hello, can you hear me?
I guess what I'll do is get out and reinitiate again. My mic says it's working, but no one can hear me, or I can't hear anyone.
We can hear you.
Let me get out.
Yeah, but you can't hear us saying
Yeah.
that.
So, okay, good.
Communication, a wonderful thing.
Hmm. Do you want me to keep recording that? Or shall I stop recording?
You may as well keep recording because
Okay,
you can always delete it later if it's of no interest.
okay.
I was going to say, I don't suppose anyone's got any idea why there are 5 platonic solids in 3 space, 6 in 4 space, and only 3 in any higher space. Does anybody have a simple explanation of that? I know it's a fact, but I don't know why it's a fact. What the simple explanation is.
What's the definition of platonic solid in higher dimension?
I couldn't tell you what the definition is. I'm
Well,
just going
it
from
certainly
sources that I've
hangs
read.
on that, right? In the case of
Yeah.
solids in 3 dimensions, the faces are polygons. So the faces could be regular solids in 4. Maybe that's the definition. So then you need to keep finding more. You have to keep doing it like that, and maybe it's the recursion that is cutting it out. If every face is a regular solid in a lower dimension, then it's becoming a restriction. I don't know. We'd have to look
Certainly
at why it
the
works.
3,
Can you hear me now?
that there are no sort of equivalent to icosahedron or dodecahedron in higher dimensions.
There's a technical
After
problem.
4.
Can you hear us?
Can you hear us now?
Sam, can you hear?